Okay, so this one's going to be a little bit different. It actually deals with material indirectly that we haven't talked about yet. But I put a note on the actual homework stuff, and I believe I've mentioned it in class as well. We're going to go ahead and work with it because we can still do that. The next section we go into is actually going to explain this a lot more thoroughly. That being said, I think we'll be fine. Pardon me? The force required to stretch a Hooke's law spring varies from 0 newtons to 32.5 newtons as we stretch the spring by moving one end 7.56 centimeters from its unstretched position. Find the force constant of the spring. Now, basically what this is saying is we have a spring, and I start pulling on this thing, and I drag it down by a displacement of 7.56 centimeters. And in doing so, I have to pull on it with a force being equal to 32.5 newtons. I apologize, I need to figure out if I can actually move where that thing is. New software. At least by my numbers. Why it says 0 to 32.5 is because up here we started a force of 0, and as I pull down, I have to pull harder and harder. But when I get to here, 7.56 centimeters, we've got 32.5 newtons. That's how hard we've got to pull. So, what we need to find is, using Hooke's law, we're going to find that our spring force is equal to negative k delta x. Right, here's where we could do a free body diagram. I've got a force shown here, but that's the force of me pulling down. What we actually have is the spring force, so if I'm pulling down with 32.5 newtons, the spring is actually pulling up with 32.5 newtons, and that's why the edge of the spring there stays still. So the main reason I bring that up is our force of the spring is going to be 32.5 newtons, but it's going to be positive because the spring is trying to pull back up to its natural length. Equals negative k times our displacement. Now our displacement is downward, so I'm going to do negative 0.0756 meters. If you use centimeters, you're going to end up with newtons per centimeter, not the SI unit and also not the units that they're looking for. Now they say that they want the force constant. That's just another way of saying the spring constant. We see here that if we keep careful track of our directions, our negatives will cancel out. If you ever end up with a negative spring constant, you've probably misplaced a negative somewhere. It'll be fine. Go track that down. But we can find the spring constant now by 32.5 divided by 0.0756. And this will give us an answer in newtons per meter. And our spring constant will therefore be equal to 429.9 newtons per meter, or 430 should be perfectly fine. So we'll check our answer. 429.9 is what they've got listed for me, so we're in good shape. That one you should be able to do pretty comfortably. The next one is where it's going to get a little bit trickier. Now, they ask the following question. There's a part 2 on this. Now that we have our spring constant, part 2. They ask, what is the work done? Find the work done in stretching the spring. Now, we haven't started studying work yet. We're going to in the near future. However, I'm going to tell you a different way that we're going to look for this. What I actually want to know, and it'll be perfectly fine for this question, that we're finding the same thing, what is the potential energy stored in the spring at this new length? Okay. It's different from what they've asked here, but it turns out that it's 2 ways of looking at the same thing, and in the next section we're going to talk about work and how to find that work. In the meantime, however, what I'm asking you is, what is the potential energy that is now stored in the spring? Well, we know that the potential energy of a spring is going to be equal to 1/2 k delta x squared. So my potential energy stored in the spring will be equal to 1/2 times the value that we just found, 429.9. 429.9 newtons per meter, times our displacement, how much we've stretched the spring out, 0.0756, I think it was, meters, quantity squared. Now, once again, if we want an answer in joules, which I'm pretty certain we do, we need to put SI in so we can get SI out. All right? This is how we find the potential energy stored in the spring, which is actually what we're looking for in this question. So I'm going to take my stretching and I'm going to square it. Technically, you may be right. There's a negative there, but when we square it, it's not actually going to make a big difference. So technically it is negative. Times 429.9 times 1/2. And we find that the potential energy stored in the spring, which will actually also be equal to the work done, but we'll talk about that later, is equal to 1.229 joules, or 1.23 joules, which is exactly what I've got listed as the solution here. So this is how we do the two parts. I apologize, on the second part, it asks for the work done, but what we're actually looking for here can also be described as the potential energy stored in the spring, so please find the potential energy in that spring.